last device is capacitor. We will study now capacitor. First, let's know what capacitor is. I will shortly define you the capacitor. A capacitor is made up of two parallel plates, two parallel conducting plates. For example, copper, aluminum. So assume that this is one aluminum plate, rectangular plate. This is another aluminum rectangular plate. When we keep them close just like this, we form a capacitor. A parallel plate capacitor. Normally, in the 11th grade, if you studied, this is going to be the first title you are going to study about the capacitors, parallel plate capacitors. And two plates are held closer to each other. So this two parallel conducting plate is called capacitor. And its symbol is like this. Two parallel lines we are drawing, which are indicating the parallel plates. And of course, these parallel plates must be connected to a device. Every capacitor, every conductor, initially neutral. What does neutral mean? Equal number of protons and electrons. So neutral means that. And this plate is neutral, that plate is neutral. Initially, this capacitor is neutral. If a device is neutral, its potential is zero. That's why potential difference between the plates is zero at the beginning for capacitor. Yeah, and we say that this capacitor is uncharged because neutral. Both plates are neutral. And when we measure a potential difference between the plates, it's going to be zero. Yeah, an empty capacitor initially has a potential difference which is zero. How? We can charge a capacitor. Yes, capacitor is a device which can store electric charge or stores electrical energy. But to store a capacitor, we have to use an energy source. Energy source is called EMF source. Then we are going to use a battery for charging a capacitor. So now I'm going to connect this capacitor to a battery. So, you know, a battery has a positive and negative terminal. So this is negative and this is positive terminal. I have to connect the ends of the terminal to plates of this capacitor right now. When I attach them like this, so this negatively charged terminal of the battery will send electrons from here to the right plate. So when one electron comes to the right plate, so right plate is charged negatively. But this electron on the right plate repels one electron on the left plate becomes positive. So as you see, charge is now it's charged. So now we can measure the potential difference. Because one plate is positive, the other one is negative. But potential difference is not that great. But still this capacitor can take more charges. Some electrons continue moving from the battery to the right plate, or some more electrons, but the electron again repels one electron from the left plate, it becomes positive again. Now what happens to the charge? Increases. Charge in the plates increases. One more electron, one more positive. One more negative, one more positive. As it is charged, potential difference increases. And finally, when all the possible places are taken, so then we say that this capacitor is completely charged. When it is completely charged, potential difference gets maximum value. Because on the right side, we have maximum number of positive charges. On the left plate, on the right plate, we have maximum number of negative charges, which means potential difference gets maximum value. But when the capacitor is completely charged, no more charge can go from battery to the capacitor. Then electric current becomes zero. So in a capacitor, electric current and potential difference are inversely changing again. At the beginning, when the capacitor is completely empty, potential difference is zero. But because it's completely empty, maximum number of charge starts moving from battery to the capacitor. That's why electric current becomes maximum. Yeah, at the beginning, empty capacitor draws maximum current, but because initially it is not charged, potential difference is zero. So when the voltmeter reaches zero, yeah, an empty capacitor, but ammeter reaches maximum number. So voltmeter reaches zero, ammeter reaches maximum. But when capacitor is completely charged, this time potential difference becomes maximum. But because it's completely charged, no more electric current can go to the plates. So when voltmeter is maximum, completely charged, ammeter is 0. It's also opposite, huh? Just like coil. In the coil it was like this again. So when electric potential difference, voltmeter is maximum, electric ammeter is 0, or vice versa. When voltmeter is 0, ammeter is maximum. So are they in phase? No, they are not in phase again. 0 maximum, maximum 0. So when voltmeter reading is increases, ammeter reading decreases. When voltmeter reading decreases, ammeter reading increases. Yani again, electric current potential difference not in phase in a capacitor. Yani out of phase. So in a capacitor, through a capacitor, potential difference and electric current are out of phase. But you know, in inductor, one of them was leading. Which one was leading? Potential difference was leading. But in here, opposite. Because at the beginning, it is completely empty. Potential difference is 0. But electric current gets maximum. Yani in here, electric current is leading. So in a capacitor, electric current is leading the potential difference. Opposite of what? Inductor. Yani this is... and they are very similar in the behavior, but this is how they differentiate. In coil, potential difference is leading the electric current, but in capacitor, electric current is leading potential difference. So then we will now check the graph again. This is how electric current and potential difference change across a capacitor. As I said, initial electric current is maximum when you start it, because it's completely empty, draws the most current. So blue is maximum, but red is 0. Potential difference is 0. Then it becomes completely charged. Potential difference gets maximum value, but because it's completely charged, no current, so current becomes 0. So then, tell me, what is the phase angle difference again between potential difference and electric current?
90.
Again 90. Again 90. So this angle is 90. Yani when electric current becomes 0 after 90 degrees, and pi over 2, potential difference becomes 0. Phase angle difference again, 90. Just like a pure coil. But only difference in here, electric current is leading, potential difference lags behind. We say lags behind. So, in a capacitor, the potential difference across the capacitor, yani VC, lags behind the electric current IC by a phase angle of pi over 2. Because we are going to write the electric current equation IC Im sine omega t, so potential difference lags behind, we have to write it by negative pi over 2. As you see, it is written in here, negative pi over 2. But when in the coil, it was positive. Now it becomes negative. Because in the coil, potential difference was leading, but now potential difference lags behind. So this is two ways we can understand how the potential difference electric current changes across a capacitor. One of them is by this graph. Second one is by these two equations. And there was a third method, drawing a phasor. We are going to draw a phasor, but this time, because this is negative, so negative in mathematics is clockwise rotation. You should rotate potential difference clockwise by an angle of 90 degrees. Now let's do it. This is how phasor related in a capacitor. As you see, electric current is phases omega t, but potential difference phase is omega t minus pi over 2 causes V to rotate pi over t in clockwise direction. So this is VC, this is IC for instantaneous potential difference and instantaneous current phasor. So any questions until here? Everything is clear?
Teacher, so there is no delay for self-induction?
In the self-induction, it was coil.
I know, but here we don't have
No,
that.
in here potential difference is 0 at the beginning because capacitor is empty.
Yes.
That's why potential difference initially is 0. As time goes, of course, it becomes charged. As this charge, this time potential difference increases. However, because it is charged, electric current decreases. Finally, it's completely charged. Potential difference gets maximum value. Because it's completely charged, electric current becomes 0. Again, they are out of phase by pi over 2. In resistor, inductor, and capacitor. All these three devices have opposition to the electric current. In resistor, it was because of the collision of moving charges with other particles. We define this resistance. But in coil, it was self-induction. Because of the self, there was an opposition. But in here, there's also an opposition. But this opposition nature is different because when the capacitor is charged, becoming charged, so it resists electric current. And when it's completely charged, electric current becomes zero. Yani, their natures are different, however, all are oppositions. All can be calculated by Ohm's law. What is Ohm's law? If I divide potential difference by the electric current, I will calculate the opposition of that device with electric current. So, VE over IE, VM over the difference, and opposition of the capacitor to the electric current, which is called capacitive impedance. So, capacitive impedance is opposition of the capacitor to the flow of electric current. Again, we can calculate it by using Ohm's law. Yani VE over IE or VM over IM is equal to XC. Again, XC has the unit of volt divided by ampere, which is equal to resistance. Inductive impedance, capacitive impedance, all have equivalent units. Volt divided by ampere, which is ohm. And capacitive impedance depends on two quantities. One of them is capacitance of the capacitor. Now, what does capacitance mean? Let me talk about this. Capacitance is how large is this plate. When the plate is larger, more charge can be stored. If the plate is smaller, less charge can be stored. Yani, capacitance is how big the capacity of a capacitance is. How much more charge a capacitor can store. Capacitance means that. And capacitance can be is represented by capital C, and you write a number. For example, 1 farad. Farad is the unit of capacitance. 1 farad. Another capacitor, 2 farads. So which capacitor has more capacitance? Of course, second one. But farad is very large unit. That's why many capacitors will have small units, microfarad. They will be expressed by microfarad. Yeah, we are going to write it like this. 1 microfarad. And every micro is converted to the SI unit, the basic unit, by 10 to the power of negative 6. So it's going to be 10 to the power of negative 6 farad. So then, capacitive impedance depends on capacitance of the capacitor. Yeah, if the capacitance is big, inductive impedance must be small. If there is a huge space for electric charges, so resistance of the capacitor will be less. Inversely proportional now. Yani as C increases, XC decreases. Of course, frequency important. How quickly you are making a change in the resistance in the alternating current also affects the capacitance. And in the equation for capacitive impedance, XC is 1 over omega C. Remember XL? It was omega L. But this is 1 over omega C. So, you know what omega is, 2 pi. If you have 1 over 2 pi FC is the equation for calculating capacitive impedance of a capacitor.
It's inversely proportional to both of them.
Yes, inversely proportional. As C increases, which means it gets very large area, then more charge can flow. That's why less position. F also, greater F means you are not able to charge capacitor completely full. If F gets bigger and bigger, that's why still there's empty space. But if F is small, and change is small, this time capacitor is quickly charged. That's why opposition becomes great. Yani greater F, smaller XC for opposition for the capacitance, capacitor to the current. A source of instantaneous potential difference, generator's potential difference is given. V equals, what is the generator equation? VVM sine omega t. I know what Vm is in here, which is 10. I know what omega is, which is 100 pi. So these are obtained from the generator equation. It's connected across a capacitor of capacitance. Now capacitance is given 1 microfarad. So microfarad must be converted to farad by multiplying 10 to the power of -6. So let's write it. C is equal to 1 microfarad, which is equal to 10 to the power of -6 farad. So when we need, we will use this. Calculate maximum value of the current. So I maximum is the question. And phase difference between the current and potential difference. We know phase difference in the capacitor, 90 degrees, pi over 2. Which one is leading? Electric current is leading. Which one is the lags behind? Potential difference lags behind by pi over 2. We know it, that's why we don't need to write it. But IM can be calculated by Ohm's law. So Ohm's law tells us for IM is equal to Vm divided by Xc. Vm is from equation we got it, which is 10. But I need to know what Xc is. Let's calculate first Xc. Xc is 1 over omega c. Omega is 100 pi. So 1 over 100 pi is 100 times 3.14, which becomes 314. So directly I am writing instead of 100 pi 314. 314. And how much is C? 10 to the power of -6. Because this is in the denominator, we have to use brackets. Without brackets, we shouldn't. So Xc will be a very big number. 3,184 ohm is the capacitive impedance. Then now insert in here and then find the maximum current. Maximum potential difference is 10 volt from the equation we get it. 10 divided by 3,184 is the Xc. So answer is electric current is very small. How much?
3.14 multiplied by 10 to the power of -3.
-3 ampere is the maximum electric current. Okay, now let's go on. Sample 6F. A source of frequency 100 divided by pi. So frequency of the generator 100 divided by pi. Let's write it here. F is equal to 100 divided by pi hertz. And effective potential difference is 200 volt. Source, yani generators, effective potential difference is 200 volt. Connected to a capacitance of 200 microfarad. C is 200 microfarad, but microfarad must be converted to farad by 10 to the power -6. And 200 times 10 to the power of -6 farad is the capacitance. Calculate the capacitive impedance. Calculate XL of the capacitor, XC of the capacitor. XC. The effective current of the circuit, yani IE. And the maximum charge accumulated across the capacitor. You don't know this as well. I will explain how can we calculate the charge. We know that capacitor stores electric charge. So we know charge symbol is Q. We just studied before when we are some whole day courses. What does charge mean? Q, symbol of charge is Q. Maximum charge is the question, so Qm I will calculate. Maximum charge stored in the capacitor. We will find this. First Xc. Let's get Xc. Equation for Xc is 1 over omega is not given. That's why I will write 2 pi Fc. 2 pi Fc. Okay. So let's insert the given. 1 over 2 pi. How much is F? 100 divided by pi. So they give this by 100 divided by pi, so these 2 pi's will simplify. This pi and that pi will simplify. Multiplied by C is how much? 200 times 10 to the power of negative 6. So don't forget to use the bracket in denominator. After that you will calculate XC. How much?
25.
100 and
25, not 100.
25.
Yes.
25 ohm is the capacitive impedance of the capacitor. Now it's calculating. IE is easy. We can use Ohm's law. IE is equal to VE divided by XC. Effective potential differences 200 divided by XC. We calculated 25 ohm. So answer is going to be 8 ampere is the effective current of the capacitor. Okay. And next one, maximum charge. Now we know capacitors stores electric charge. We know that. And there's an equation. There's an equation for calculating charge stored in a capacitor. This equation, Q is equal to C times V. Yani capacitance of the capacitor and also potential difference across the capacitor. Because maximum charge is the question, I had to use maximum potential difference. Maximum potential difference is needed. Capacitance is given, but maximum potential difference must be calculated. So effective potential difference is 200. Because I have to calculate what maximum potential difference is. Maximum potential difference, effective potential difference multiplied by root of 2. So effective is 200 multiplied by root of 2. It becomes 278. How much?
83.
83. 283 volt is the maximum potential difference. Then insert this maximum potential difference in here. So maximum charge stored in capacitor is C is 200 times 10 to the power negative 6 multiplied by maximum potential difference 200 and multiply that
Is 0.0566.
66.
No, 10. 0.0.
0.0.
Yes.
0.0566. What is the unit of electric charge? Coulomb. Okay. It is represented by C or Coulomb. You write it like this. Okay, this is one of the Mr. Exam question. Calculating the maximum charge stored in the capacitor.